this is Kshitij, and on this channel we talk about robotics, research and academia. If you're new here, this is another lecture of the lecture series TT102 Intro to Python for Robotics, where we are learning Python in the context of robotics using the ROS2 framework. So the focus of today's lecture number 6, is understanding URDF in ROS2. So this is our code base that we've been developing over the past few lectures, and if you remember, we had this TTBot.urdf.zacro file. It's an XML file, but we never went through it in detail to try and understand what's a URDF, and that's specifically the focus of today's lecture. So first things first, let's understand what is a URDF. So URDF stands for a Unified Robot Description Format. As I said, it's an XML file, as you can see right in front of you. This format is essentially used to describe the structure and a visual representation of a robot. So they have a few key components, as we'll go through them in just a second, but typically they are links and joints that represent, physical parts of a robot. So imagine your arm. So this forearm basically is a link. Your wrist is a joint, your elbow is a joint. So you have like joints connecting links, and links are like rigid parts that they themselves do not bend and move, but through the joints, two links are connected to each other. Then there are inertial properties of components such as center of mass, inertia, that link properties for each of the links. And they're crucial for simulating the dynamics of the robot, because the simulator that we're using, especially Gazebo, is a physics-based simulator. So you have properties like mass and inertia. Then there is also visual and collision representations, because each link has some sort of a visual representation, and collision describes like the collision detection during the simulation. Could be a cylinder or a cube surrounding the joint that represents the collision kind of bounding box around it. There are some Gazebo related properties that would be encapsulated inside a Gazebo tag, and there are some material properties that you use to explain the appearance of the robot, so some different colors and stuff. Then of course there are sensors and actuators that we're going to go through in just a second. So let's start going over our URDF file and try and see what is where. So first things first, because it's an XML file, so you have this tag here. You start out with the name of the robot, so we've decided to call it a TTBot. We'll get to this link, it's a special link, we'll get to it in just a second. Let's start out here. So as I said, there would be links and there would be joints, and then there would be properties, right? So we have a chassis, and that chassis has some inertial properties like mass, and has some collision properties. So we have basically it's a bounding box around the chassis, and the chassis itself for the TTBot is like a cuboid of sorts, right? So this is the length, width and the height properties. Origin, what you're seeing here basically is the offset along the XYZ axis and the roll pitch yaw. So how you want to position your visual components with respect to a fixed frame of reference, okay? And that fixed frame of reference is essentially this. Typically you call it base footprint, but I borrowed this off a Gazebo repository and they decided to call it a robot footprint, but it's more or less the same thing, right? Then aside from the chassis, we have 4 wheels. So there is a left wheel, there is a back left wheel, then there is a front right wheel and a back right wheel, okay? And each of them have similar properties. So there's going to be mass, there's going to be origin, there's going to be inertia, and visually we have represented them as simple cylinders. We're not going for super fancy geometry, but a cylinder with certain length and certain radius. And then they have the collision properties as well. And as I said in one of the previous lectures, we have 2 sensors on this TTBot. One is a camera. So again, camera also you need to have some sort of initial properties and a visual representation. So we have it as again a cube. So there's like not like an actual webcam looking like camera, but just a cube on the robot. And then similarly, Hokuyo, this is our LiDAR. So it has the same properties. Anytime you see a .dae file or a .stl file, these are known as the mesh file. So if you have a mesh for a certain component, this XML file, the URDF file, allows you to import the mesh of the object as well, and DAE is a collada file. .stl is like an STL file that you get from things like Blender or SolidWorks and stuff. So you can also import them here that help you visualize your components. Now, thing to note here is, the joints, as I was saying. So there is a wrist joint, which is a revolute joint. Then this is a kind of 1 degree, 2 degree of motion joint. There could be a linear joint, angular joint, and so on and so forth. So here, wheels basically, because they continuously move, so we have a continuous joint. Think of this as a revolute joint. Let's see what other joint types we have. The other joint type should be a fixed joint. So we have continuous. So 4 wheels, they are all continuous. C, fixed. Something that does not move. Of course, a camera does not move and a LiDAR does not move. So they are fixed joints. And I think this should be it. There's no other joint type that you need, at least for this robot. So there is a, hang on, let me open the wiki real quick. So found the wiki for ROS 1, but the principles are more or less the same. So as you can see, the joint attributes has a few different types. So there's a revolute joint, which is same as a continuous joint, but you have a min and a max. So if you don't want a min and a max, you can use a continuous joint, which is what we are using. There's a prismatic joint, so it would be like a slider. Then there's fixed, that the components don't really move. If you have a 6 degrees of freedom joint, you have a floating joint. And if you have a plane perpendicular to an axis of motion, then you have a planar joint. So these are the couple of joints, but most of the time in mobile robotics, I've only used like fixed and continuous are the commonly used joints, because you have wheels, propellers kind of things, and then there's the chassis. So going back to our URDF, so this is what we have. Basically inside the URDF, we are not reading a direct URDF file, we are reading a Zacro file. So Zacro file basically is like a macro wrapper around the XML file. And because we have passed this Zacro file as a parameter to the launch file, we don't necessarily have to compile it as a URDF, even though I have a script that also compiles it and spits out a URDF. So let me just show you how all of that works. So we are here. If I go here, so you can see in the bottom there is this compile zacro.py file. So if you want to forcefully run through this urdf.zacro file and compile a .urdf file like I've done here, this can be done, although it's not necessary, because if you look through our launch file, the one where we are spawning here, so this is basically already taking the Zacro file and then passing this as a parameter to the state publisher, and then that's how you're able to visualize the robot anyway. And let's see what we have inside the robot description. So here we have already defined the paths of the Zacro. You see the TTBot.urdf.zacro file, so we are parsing it, and then we are passing it as a parameter to the node robot description. So we don't necessarily have to parse Zacro to a URDF, because it's a wrapper and more cleaner way to parse to a URDF file. And you can also do some math in here if you want to have some computations like multiplication, division, addition, whatnot. But right now we have a very simple Zacro file. Okay, and let's go back to the special joint that I was telling you. That was this is normally where your URD file has to begin with. You need to define a base footprint. This, as you can see, is a virtual joint. So virtual link, sorry. And then the joint basically has two components, a parent link and a child link. So it is basically saying that the robot footprint is the parent of actually everything, and then you have childs for it. So for example, chassis is the child of robot footprint, and then the wheels would be the child of the, so base link would have all of these childs, right? So how do we know what this structure looks like? What's the parent, what's the child, if you're doing something right or if you're missing something or whatnot? So for that, there is essentially, if you go through this cheat sheet, I've put this here as well. So this utility tool is very useful for you to execute and visualize this tree structure and try and understand who's the parent and child kind of relationship and what's happening. So when you run through this in the terminal, what it's going to do is it's going to listen to the TF data for like 5 seconds. It will generate a graph called frames.pdf in your root, and that you could kind of go through to try and understand what's happening. So as you can see, there's a frames.pdf here that I've opened here, and what this does is basically, this is now you're able to visualize, right? So robot footprint is the parent, which has the child chassis. Chassis has 2 components, camera and the lidar. As you can see right now, the wheels are completely missing from this tree, which is not something I think is right, and I'm still debugging this and how to fix the tree structure. But that's why this is a very essential, important tool, so that you can figure out if you have all the transformations that you need. And you also get this timestamp of the transformation when the transformation was achieved. So what this is also telling me, 0000, is basically you might have stale transformations. So we are also going to look into that to try and see like how do we get the most recent transform, which is basically, you know, with respect to the chassis, where is my camera? With respect to the chassis, what is my left wheel kind of doing? What is my right wheel doing? What's the position? What's the orientation? And so on and so forth. So while these things are always fixed on a robot, so with respect to the chassis, the camera and the lidar don't move, the wheels do move. So you need like a real-time transformation of where those things are. If you try and run this utility, sometimes on some of the videos you're going to see they just do ROS2 run TF2 tools view frames.py. If you do that, you're going to get this error. So initially I also forgot about this, and you're going to get this error, no executable found. Okay, if you see that, you have to do 2 things. One is to go to the package install bash script of mine and run through it, because you might be missing a ROS and then your ROS distro TF tools package itself. If you already have it, which means when you run this command it did not install anything and you see install completed, what you have to do is to make sure that you are typing frames.py. That's when it executes. So sometimes, I think in one of the previous ROS distros, or up until a certain point, it used to be just view frames, but at least in Foxy and onwards you have to do view frames.py, and only then it executes and figures out what you have to run, right? So this is an important utility. So now what I'm going to do is try and look through this TF tree that we have and make sure all the components are in the right place, and then we'll continue the lecture from there. Okay, so finally everything is sorted. As you can see, we start to see our robot inside our VNC. So what you should see technically, so this simulator is an Rviz robot visualizer. It's an in-house simulator that comes with ROS. Okay, so robot model is basically your URDF structure, so boxes and cylinders and stuff, and TF is basically the transformation tree. So you see all these frames that are here. Let me try and minimize this. Okay, so you see all these frames that are here, and you see the arrows that are pointing. So basically this yellow dot in the center, this one, is your the main frame of reference. Then everything is with respect to this. So for instance, if your wheel, so for example, this is the left front wheel and this is the right front wheel. So with respect to the base frame, where are they? These are the rear wheels, so they are all pointing towards the base frame. The sensor with respect to the frame of reference is where. Okay, so this basically helps you visualize what is where. And the reason why we were not seeing the entire transform tree was because by default, Rviz looks for a base footprint as the virtual link, and the base link as the virtual link. But that does not exist, because in the URDF we have a robot footprint as the actual, the frame of reference. So I had to tweak that. And the way we are able to visualize something like this is through a tool. So let me show you what that tool is. There you go. And in this source code, basically what I added was, where is the package install? Right. So here I added another tool, URDF tutorial. So what this does is essentially allows you to launch Rviz with the absolute path to your URDF so you can visualize what is going on. Okay, you will run this package install.bash script. It will install everything. Then you have to launch this command now. So ROS2 launch URDF tutorial. There's a display.launch.py inbuilt, and you have to give the absolute path to your URDF file. So inside the package, our URDF is inside the URDF folder, and it's called TTBot.urdf.zacro. So as you can see, even though I've compiled the .urdf file, I'm never really directly using it. I'm fine with using the Zacro because Gazebo and our launch scripts know how to parse a Zacro to get the URDF information they need. Okay. So then you put that in the terminal here, and you're going to see these warnings, right? Invalid frame ID base link. So you just have to make sure that it's getting the correct frame. So when you click on robot footprint, it will start to show you the robot as you were seeing. And you see this has also updated now. So it has a proper hierarchy. So the robot footprint is the root of the tree that has one child, the chassis. Everything else is with respect to the chassis then. So the camera is a child of the chassis, the LiDAR, and the four wheels. And as you can see, this is a kind of static transform, right? So we don't really care when that came from because the base footprint and the chassis, they are not going to change yet. But everything else, you need like a real-time transform backwards all the way to the root because the robot can start to move. Okay, that's why it's like the timestamp transform, when was the latest transform that you obtained, and so on and so forth. Another cool thing with this URDF tutorial package and the way we are able to visualize this, let me quickly switch back to here. So inside Rviz, as you can see, there is a utility. So let me bring back the robot. Okay, so this is our robot, and as you can see on there is a LiDAR here and there is a camera here. So it's all visible to us, and if you don't want to see the TF tree, you can see just the robot like this. Okay, so it's like 2 sensors, 4 cylindrical wheels, 1 cuboidal robot chassis. The joint state publisher is the one that is taking all of these joints and publishing it. So when you kind of, if you want to mess around with it, okay, let me visualize the TF so you can see what is happening. So keep an eye out on the front left wheel. So you see this one is rotating, and notice that these angles are in radians. So it's like -pi to +pi. Okay, everything is in radians here. Front right wheel, so you can see that it's a revolute joint, so it's moving properly. You can randomize and move all 3-4 wheels at the same time. You can center to reset everything. Okay, so you can play around with it and try and understand whether your joints are working properly or not. And notice how it is giving you controls for the wheels. Well, of course, for the front wheels right now, because the GUI only has these. Oh, there's also the back wheels here. So you can mess around with these, you can mess around with these, because there's only 4 revolute joints. We have 2 fixed joints, the camera and the Hukoyo LiDAR sensor, which of course don't move, don't rotate, don't twist around. So you're not going to see controls for them. Okay, so this was like a quick run through of what the URDF file is. Oh, and one more thing, if you really want to mess around with the naming conventions and change the names and stuff, so it's here. And in this source code, you have to make sure that you go through this .gazebo file, because this is the differential drive controller. So we have looked at skid steer controllers. I've written blogs about it, and then this is basically a control mechanism for controlling the 4 wheels. And in here, basically, it's giving out the joint names for the 2 left joints, the separation between them, the diameters. The 2 right joints, separation between them, and the diameters. Remember, it's a cuboidal, so the separation should be the same, the dia should be the same. Otherwise, you might have 2 big wheels and 2 small wheels. You're defining a torque, and this is where, so robot base frame, so this is where you let the Rviz and Gazebo know what is the base frame of the robot. Okay, since this is a .gazebo file, Gazebo would understand the base frame is robot footprint, but if you only change the base footprint name here as base footprint and base footprint joint, Rviz is going to start throwing this error that it doesn't know what the base link is. Okay, So be very careful with the naming conventions and be sure that you're doing all of this in the right places. And if we go back to our VNC window where we have the robot, one more thing that you could do is you could go to File, you could save config as, and we have this, let's see, not URDF tutorial. We go to our, okay, this is our workspace, go to src, spawn package inside Rviz, and we can save this as officeworld.rviz. Okay, so next time when we basically spawn our robot, we can pass this .rviz file as a config file to our launch file. So I've already started preparing something like that. I'll give you a quick sneak peek. So this is our spawn TTBot pose.launch.py. Basically the idea here was, in one of the previous lectures, we spawned the robot at a particular position and orientation inside the Gazebo office world. So it's the same file. And what I'm doing now is, you see this bit here. So it's basically taking the office world.rviz file and it's passing it to the Rviz node, and it's basically passing that as an argument and spawning all of that information inside Rviz as well. So you have the robot visualized inside an office environment with 2 sensors, and we have the robot also spawned inside an Rviz. So you have the robot model there, but what we don't have is the 2 sensors. So let's also open that inside using this URDF tutorial tool and also see what the sensors look like inside Rviz. So for that, we go inside our Rviz. So this is how far we have come. You can uncheck TF if you want, but I leave it checked on. So the way you add the camera, the sensor feed in general, is you go to add a new display button here. You look for camera. So we want to add a camera. So we're just going to call it a camera. We're going to press OK. There's an error, basically because there's an error because we just subscribe to the URDF. So Rviz has a URDF, but there is no ROS node yet that's publishing to the camera. So we have to write a sensor node that basically publishes sensor information there, and then you can come here and you're gonna have a topic that you could subscribe to. So right now the status error is basically saying that it has an empty topic. You see, empty topic name, so it doesn't know what topic it needs to subscribe to. Okay, nonetheless, we're going to add all our sensors that we want. So let's see, what else do we want? So we want a laser scanner, laser scan. Okay, laser scan, same problem, nobody's publishing there, so it doesn't know what to show you. But anyways, we have that, and then we're going to add, let's see, what do we want to add? A map. No, we're not making a map yet. We're gonna show, well, technically you could show a range because you are sensing a range sensor, but again, all of this is the same problem. Okay, let's remove everything else for now. So we know we have we can add odometry. Odometry, where is odometry? Odometry. So you have nav messages, odometry passed around, so you can publish those things as well. So basically we have sensor values, so camera and laser scan for now, because we have a Hokuyo laser scanner and a camera on board the robot, but nobody's publishing to it. So let's go back and save this config. Let's be sure that it's resaving on top of the office world because it did not give us a warning. We go to Rviz, save. Yes, I want to replace it. Okay, fine. So in the next lecture, what we're going to do is we're going to pass this as a description in the launch file. As you've already seen, I've set everything up. We're going to spawn the robot inside Rviz, and we're going to write sensor nodes that publish some sensor information to the camera and the lidar, the Hokuyo laser scanner, and we're going to see that inside Rviz. So the difference between a Gazebo and an Rviz is Rviz typically helps you visualize the sensor feed, and Gazebo typically helps you visualize the environment. So for example, if there's an obstacle in front of your robot and you have a laser scanner sensing the distance to it, All of this happens inside Gazebo, and inside the Rviz you're going to see some sort of a point cloud. So that's basically going to tell you, okay, I see some obstacle, I see some free space. You're going to get a 2D camera feed, so what the robot is seeing. So you see at the bottom there it says camera, but nothing inside, because of course it doesn't have a topic to subscribe to, which is publishing information from the camera. So all of this is what we're going to look for in the next lecture. But I hope with this lecture you get a basic understanding of what a URDF is, and if you want to customize this robot. For example, a simple customization could be you could have a laser scanner, one in the front and one in the back, because right now a laser scanner at best would have a 270-degree sensing radius. Okay, we can add a sensing radius in front of the sensor so you know what that looks like. We'll do it next time when we start seeing the sensor feedback. But you could also have a Hokuyu laser scanner at the back of the robot, because technically if you have a 270-degree sensing cone, the back of the robot is completely blind. It doesn't know what's happening. So normally the robot goes forward and then turns, so it basically never reverses. But nobody's stopping you from reversing if you have some sensor feedback from what's happening behind you, so you're not running blind. So depending on your application, you could add more sensors, you could move things around, you could customize the stuff. So that's why understanding what a URDF is and how you can add, subtract things to it is very essential. So now we've gone through the basics of the URDF. Next time you could try and mess around with it. Okay, so you could add, subtract stuff, and if you do make some customizations, make sure to make a pull request to our GitHub repository, so that with proper details of what you've done and a GIF showing how it looks like inside Rviz and in the Gazebo environment, how it looks like, so that others could then make a pull request and clone that repository with your add-ons. You could make a separate branch for it with call it something more sensible like customized robot or whatnot. So with that, we're going to end this lecture for today. I hope it was useful and you have a decent understanding of what a URDF is and how to spawn a robot from a URDF inside Gazebo and Rviz, which are typical tools that we use when we are building simulations for robots. And if you have some custom robots, so if you are an expert in SolidWorks, for example, you could design your own custom robot, export it from there, follow the same procedure and import it here and spawn it here. So you can start seeing your own custom robots, and you could have a multi-agent system as well, right? So that's a problem for another day. We will do some separate course on multi-agent systems. So we have multiple robots spawned in here, same copies of multiple robots and multiple different robots, but that's for some other day. Anyways, gonna end this lecture series here, and we're gonna talk about some more fun stuff in the coming lectures. Until then, be sure to like, share and subscribe. See you again the next time.